Howdy, y'all. I'm sorry about that. Apparently, I can't seem to tech today. Um, I am a little bit behind. I had to run in with some street preachers and just trying to settle myself. And I was thinking about actually postponing this, but I was like, nope, nope, I'm gonna do it. So anyway, if you'll bear with me, I will. I need to find my slide deck. Ye old slides. Because today we are going to talk about, one of my favorite subjects about astronomy, the toys. I'm a boy and his toys. We're going to talk about telescopes. Is this one? How about that one? Hopefully this has got the slides I want. Yeah, I think this will do. I think this will do nicely. Present. Let's go with slides. Slides. Telescopes. Open. Long time no see. Howdy, Nimrod. Yes, Clive, my alien hunting gear. So I actually just went up there fairly in the last half hour or so and got that data that I took last night. For those of you who don't know, I did a live stream earlier this morning for me and taking data on M13, the globular cluster in Hercules. And at some point, when I have the free time, I will do another stream where I analyze that data and talk about what I find. So, spare change. All right, so let us. Okay, well, apparently that doesn't like that slide. So let's talk about telescopes. Let's because essentially what I'm going to be discussing today, and this lecture brought to you by Starbucks Frappuccinos, is, like I said, telescopes. Essentially, what are the instruments that we use, that astronomers use to collect the data that we then analyze and interpret in order to find out things about the universe? As I mentioned in my other lectures about light, almost 95% is my made-up number. 95% of everything we know in astronomy, we know because of the collection analysis of light. Well, what is it that or what instruments do we use to actually collect that light? That is pretty vital, this whole operation. We use primarily telescopes. And I'm going to be primarily dealing with optical telescopes, or I'll be describing optical telescope designs, but I'll also go a little bit into radio, and I will also talk about interferometry. What I really won't cover are the higher energy telescopes like X-ray telescopes, gamma ray telescopes, UV telescopes. Those are a little bit more sophisticated because they are dealing with such higher energies. The optical systems involved are a little bit more wonky, and as I'll talk about before, there are certain limitations on how you can actually do how you can actually do that kind of science. But what are the three main goals of a telescope? And as I like to say, I'll use the old sort of racy joke, bigger is better. For an astronomer, that is certainly true. You want the biggest telescope you can possibly get, which is why we are constantly building bigger and bigger and bigger telescopes, to the point that on the horizon, the Americans are trying to get the TMT built, the 30-meter telescope, which is a telescope that is going to have a collecting mirror of 30 meters. The Europeans are going to outdo us by putting together the ELT, the extremely large telescope, which will be 40 meters in size. Hopefully that gives you also a little bit of an indication as to the creativity that astronomers put into naming telescopes, ELT and so forth. But the reason why we build bigger telescopes, there are really two primary reasons. The third one is the larger the telescope, the more clearer focused the image is. But really the two that I'm going to harp on is that a telescope, if nothing else, a telescope is a light bucket. It is what actually receives the light. So you want as large a bucket as possible in order to collect as much light, because the more light you have, the better your data is going to be, the more you can get out of it. More specifically, the larger the light collecting area of a telescope, the fainter you can see. So one of the reasons why JWST, for example, which is a 6-meter telescope, is doing such amazing work and really surpassing what Hubble has done is that it's 3 times larger than Hubble. The JWST has a primary mirror of about 6 meters, whereas Hubble had a primary mirror of about 2 meters. And so that light collecting area, that increased aperture, as we call it, is allowing the JWST to see to these farthest reaches of our galaxy, or really the very beginnings of our galaxy 13 billion years ago. So it is the fact that it's larger that we can do that. The other thing that I'm going to be talking about is something called angular resolution, which is the fine detail that you can see using a telescope. The larger the telescope, the better that fine detail, or the finer the detail you can see in any particular object. Collecting area and aperture. Well, let me first describe or define what an aperture is. A telescope aperture is the size of the primary piece of glass. It is either what we call the objective lens for refracting telescopes, or the primary mirror for reflecting telescopes. The aperture is the size, or the diameter rather, of that piece of glass, be it a lens or be it a mirror. And when we talk about telescopes, we will often refer to them, unless they have a proper name, we will refer to them by their aperture size. So for example, I often refer to the telescope that we have here on campus as the 32-inch telescope. What that means is that the aperture of the telescope is 32 inches, or the diameter of the primary mirror is 32 inches. Yes. Well, actually, you'd be surprised, Nimrod. We academics actually do know how to use metric. Like I said, our telescope is in meters. So, although, like I said, the telescope here is in inches. I don't really know why. I've been trying to train myself to get into to refer to all things as metric, but for some reason with this class of telescope, I just can't call it a 0.8 meter. It just doesn't feel right. And I don't really want to call it an 80 centimeter telescope either. It just doesn't feel right. Anyway, I'm diverging. So an aperture, as I said, is that large area. And again, my equations aren't putting up, but essentially the amount of light that you get is proportional to the area of that telescope. So it goes as the square as the diameter. So if we go back to the JWST and the Hubble example, JWST is roughly three times larger than Hubble, so it collects 9 times more light than Hubble does. So that helps illustrate, or is one of the main reasons why the JWST can see so faint in the night sky, because it's literally collecting 9 times the amount of light that Hubble did. Sorry, I looked at my Discord and I'm actually seeing a message from Dr. Nimrod telling me that Ireland cheated France out of a rugby game. Anyway, let me just minimize that so I don't get distracted. So next thing we're going to talk about is angular resolution. Angular resolution is, in my experience, is something that can be often misinterpreted. What angular resolution means is the ability to see fine detail, as I've said, or more generally, or rather more specifically, say you have two objects, say you have two stars right next to each other. Depending on your angular resolution, you might be able to see them as two individual stars, or they may actually clump together and you would only see basically one solid object. So the higher the resolution, the better your ability to distinguish two objects that are close together as two separate objects, or as you can see in this example, these are two, I can't remember what the actual name of this object is, but it is a planetary nebula with a white dwarf in the center, and then you have this gaseous envelope around it. The one on the left, that is an image using a telescope that has a smaller aperture. You can see that there is something there. You can see the glow from the central star, and you can see that there is some kind of nebulosity around it. But it's only until you get a larger telescope with an improved angular resolution that you can really start to pick out like the filamentary structure within that nebula. And so that allows astronomers to better find out what is going on in those individual particular regions, to find out what exactly the science behind why those, for example, those filamentary structures exist. So when it comes to angular resolution, the smaller the angular resolution, the better. So for example, if I have a telescope that has an angular resolution of 1 arc second, as opposed to a telescope that has a resolution of 1 arc minute, what that means is that the telescope with 1 arc second can distinguish two individual objects as being separate if their spacing is 1 arc second or greater. The telescope with 1 arc minute, that means it can only distinguish two things as being separate if their separation is 1 arc minute, 60 times larger than the arc second. If it's closer to that, in either regard, if it's closer than that, you cannot distinguish them as two separate objects. They will glom together, or for example, in this, instead of seeing those filamentary structures, you will just see kind of washed out as just a broad sort of nebulosity. Angular resolution is so. Let me second. Where? Aha. So the equation for angular resolution is this. Theta is the angular resolution. 1.22 is just simply a constant factor. Lambda up here is the wavelength of light. D is the telescope aperture. Now, on the slide, I say that lambda and D are in meters. Really, it can be in any length unit, so long as you're consistent. So it can be both in meters, both in centimeters, both in microns. It doesn't matter so long as they're both equal, and basically that unit goes away. And then finally, what you get is this angle theta is in radians, which you can then convert into degrees or in arc seconds or what have you. So this is a simple definition or simple description of angular resolution. So what we're seeing here is the relationship that I really want to point out is that the angular resolution is inversely proportional to the aperture size. And again, remember, smaller the angular resolution, the better, the finer detail that you can see. So if D increases, theta decreases. So bigger, better. But you also have this figure of lambda, which also comes into play. It also comes into play, meaning that if you have, like, for example, our 32-inch telescope. Actually, this is kind of a counter example, but bear with me. With our 32-inch telescope, we are in the process of installing an IR camera, a camera that is sensitive to light in the IR part of the spectrum, or the redder part of the spectrum, than our normal camera is, which is in the visible. With our telescope, I can't really. You at home can run the numbers if you want. The middle of our visual camera is around 500 nanometers. So if you convert 32 inches into nanometers, you can do the math. You can figure out what our angular resolution is. Our theoretical best angular resolution that you can do. But that angular resolution is only for that, like I said, if we're in the green, that angular resolution is only for the S-big camera or our main camera. For the IR camera, the wavelengths we'll be looking at are going to be much larger. So our angular resolution is actually going to suffer when we use that IR camera. So the angular resolution of a telescope also depends on the type of instrument or detector that you were using, or the type of detector that it uses. So, for example, and I'll explain this. I'll get into this a little bit more in detail later. Radio telescopes have horrible angular resolutions, which is why they are so large. When we talk about radio telescope sizes, we're no longer talking about meters. We're talking about tens to hundreds of feet. Although I guess you could say meters, but again, Americans and their imperial units. But anyway, I think we have a flat earther in the audience. Cut the blue marble in half in order to astronomers cut the blue marble in half in order to map the star. I'm not sure what that means. Renee, if you want to expand on that, please do. But I'm going to keep going. So, what angular resolution? And this is kind of the confusion that I've seen is the difference between resolvability and detectability. So, for example, if you have a star up in the sky, unless you are using a very specific technique or you're looking really at a very specific star, almost all of the stars in the night sky are going to be unresolved, meaning that you will not be able to see the actual surface of the star in question. All you will be able to see is the bright light coming out of it. So objects in astronomy are frequently detectable, but not resolvable. We can't see the detail of the object, but we can tell that the object is there. So another example, a more terrestrial example, is if you're on a lone desert highway and you see basically headlights behind you. When you first spot them, you may notice that it only appears to be a single light. But as the driver approaches you, the distance between the two of you gets better or it gets shorter. Your angular resolution improves. And so those two lights actually split out. And instead of one light you're seeing, you now see both lights of the headlights. And then it goes past you or what have you. So again, there's a difference between the resolvability or the diffraction limit of a telescope and the detectability, or how faint you can see with a telescope. No, I am not. I will spare you all the gory details of the probing. It's not for the faint of heart. So, what are the kinds of telescopes that we have? Well, we have two major kinds. We have refractors, which use lenses, and then you have reflectors, which use mirrors. Now, hopefully, I'm going to try something new. Hopefully, this will work. I'm a little bit worried about the sound quality, but let's go with it. All right. Hope you all can hear me, and I hope, I hope I don't break this. Hope you all can hear me, and I hope you all can see this. Maybe if I turned that on. I don't know if you can see very well. Black isn't greatest, but this is a refracting telescope. What we have here is we have and this is, I believe, look at it, 80 millimeter? Yeah, 80 millimeter objective. So we have a lens which is located right here, a convex lens, located right here, and the light comes in, hits that 80 millimeter diameter convex lens. That light gets bent along this tube, and then we have down here, we actually have what is called the star diagonal, which is basically just a flat mirror. Basically, you have light comes in through here, hits a flat mirror here, and then gets redirected up to the eyepiece. But same basic principle applies. The light comes all the way through, and you have a detector at the back end. Another piece of term that you'll want to know is focal length. The focal length is the distance between the primary, or its objective lens, and where the image is going to come into focus, or in this case, where the image, or where the light is actually going to be focused by the eyepiece. That is what is known as the focal length. That's going to come into play when we talk about the advantages of one type of telescope versus another. So this is a refracting telescope. This is basically what Galileo used. It is the simplest form of telescope that you have. The problem with well, I'll get into the problems in a moment. I want to talk about, I do want to give you a little anecdotal story. I don't know if it's true, but I want it to be true. As the story goes, so you may or may not know this, but Galileo was in fact not the person who actually invented the telescope, although it is somewhat regularly attributed to him. The person who actually, we believe, developed the telescope was an optician by the name of Hans Lippershey in 1609. What Galileo did can be credited for is that he is the first person on record to actually point the telescope to the sky and make observations of heavenly bodies using this instrument. And his was a bit smaller than this, but basically roughly the same size. Well, as the story goes, Galileo wanted to build this instrument back in the early 1600s, around 1609, 1610. These aren't cheap. Grinding those lenses was a laborious process. It was also required a great deal of precision given the instruments of the age. And so he needed money. Galileo needed money in order to build this thing. So he went to the Um, he went to the, I guess, the Duke of Florence or Doge of Florence, I don't know, the leader of Florence, and he said, "Hey, can you give me some ducats so that I can build this thing?" And the Duke was like, "Well, that's nice, but what are you going to do for me?" And Galileo thought about it and said, "Well, if you fund this, if you give me the money to build one of these, then I will give you the plans and you can build your own and you can use them to spot enemy troops coming to you far sooner than you could with your naked eye." And so that is one of the earliest stories that I know of the marriage that is still today between science and the military. So the telescope was actually a military funded device when it first came out. The other thing while I have this out is I want to point out the mount. And again, I don't know how well you can see this, but essentially you have two axes. You have this axis here, and you have this axis here. This axis here. So you have this axis and this axis. They are orthogonal to one another. And what these correspond to, if you remember a few lectures ago, I talked about coordinate systems. This corresponds to I know there's a clutch around here somewhere, and I just can't see it, but this corresponds to RA, or right ascension. So, in order for this is what's called an equatorial mount, or more specifically, a German equatorial mount, because it has this nice counterweight that if you have a large enough telescope, you will bang your head up against it, or in this case, your knee, because the Germans hate us. So, this is an equatorial mount, meaning that it uses equatorial coordinates, right ascension and declination. So you need to get this aligned very, very properly. It only works if this axis here is pointed directly at the North Celestial Pole, or for you weirdo Aussies out there, or South Americans or Africans, the South Celestial Pole. Only works in that case. So this tracks in right ascension, and then, I'm sorry. Yeah, this tracks in right ascension. The other one tracks in declination, stellar latitude. So this is an equatorial mount. So that's your refractor. All right. So, like I said, Galileo's time. This little cutie, hey, Georg, this little cutie, it was invented actually by Isaac Newton, and is given his name. This is what is known as a Newtonian telescope. So, Newtonian optical design. I'm trying to figure out the way this works is that it is a reflecting telescope. It uses mirrors to reflect to your eye. And this one is actually approximately the same size that Newton first built. This is about a 4-inch aperture, or 114 millimeters for all you weirdo metric people out there. So what happens is light comes down through the top of this tube, comes down through the tube, hits a mirror down here. That mirror then focuses the light up to a flat mirror here, often known as a secondary mirror, and that light gets redirected out to the side to, in this case, an eyepiece, or you can put a camera or any sort of detector that you want over here. So this is what is known as Newtonian optical design. Like I said, it uses a mirror mirrors to reflect the light to your detector, and it also, and so we can see here one of the advantages of a reflecting telescope to that refractor over there. And the difference is This is essentially a straight optical design or a straight optical system. The light comes in through the top, goes through the telescope, and hits the bottom. There is no way to make a refracting telescope where that focal length can be folded. That is where the mirrors come in. That is where the reflectors come in. This is what is known as a folded optical path. The light goes down, then gets redirected up and then out. Here, the light comes in and goes all the way down, and that's it. Generally speaking, when you make telescopes larger, when you make this mirror larger or make this lens larger, what happens is that your focal length is going to also improve, or excuse me, is also going to get larger. So you can imagine that if I make this thing much, much larger, this tube is going to get much, much larger, and then we run into a structural problem. This is also on a German equatorial mount, which we actually don't use professionally anymore. We actually use what is known as an alt-as mount, but I'll get into that in a moment. Size matters. Yes, Flo Rida. Truer words were never spoken. Real Cygnus. That is an excellent observation, and which I will actually talk about. Oops, no, add. Here we go. So here are some. Here are the diagrams. Here's basically schematics or diagrams of what I was just yelling at you. Is in the top you have the refracting telescope, you have the objective lens, and then you have the eyepiece. In this case, you can see that, hopefully you can see that with more modern telescopes, with more modern refracting telescopes, they become achromatic. They actually use two different lenses to solve one of the most common problems of a refracting telescope, and that is what is known as chromatic aberration. If you take a prism, you shine white light through it, what happens is you get this rainbow pattern of color because blue light refracts more than red light. Same thing happens with a lens. A lens is really just a place where light gets refracted, and so in general, the light is going to get refracted to a point into a focus, but that focus is going to be different, discretely different for each individual band or color. So if you look at a really bright object, what you're going to see is you're going to see that like Jupiter, and then surrounding it, you're going to see blue, then yellow, then red, kind of coming off of it. So that's chromatic aberration. You can make what is known as an achromatic or achromatic refractor, like an apod or something. I can't remember what anyway, an achromatic refractor by using two different lenses to basically minimize or mitigate that effect. And then the reflecting telescope is down here. Now there are a couple of other types of reflecting telescope, which if a slide doesn't show up to show you the optical systems of that, I will hopefully remember and come back to it. But let's talk about refractors for a moment. All major telescopes, definitely modern research instruments, are reflecting for a couple of different reasons. The one of which I've already described, which is the fact that the larger you build the telescope, the larger the aperture of the telescope, the longer the tube. Do I have? No. Nope. All right. Well then, poop on this. I'm actually going to find the images. What? That's not what I wanted. Stupid website. Let's try this. That? All right, that'll work. No, I don't want your stupid book. All right. Again, apologies for the. So this is the Yerkes Observatory. The Yerkes Observatory has the distinction that is the home of the largest refracting telescope in the world to this day. It is the Yerkes Observatory is part of the University of Chicago. It's somewhere in. It's actually not in Chicago at all. It's a little bit outside of this, or actually quite a bit outside of the city. Hold on, let me accept these damn cookies. It is a historic. It is a historic instrument, but you can see, and hopefully you can see that this over here at the bottom of that white tube, you might be able to see a wee person. So that gives you a sense of scale as to how friggin' long this telescope is. And so you sort of, if you were to build this even larger, you have this sort of, you will have a structural integrity problem because the tube itself will sort of bend under gravity. But actually, as it turns out, it's actually kind of impossible to build a larger telescope to this. Oh, real quick. I love the Yerkes Observatory. It's on my bucket list to go see because what's awesome is you may notice right now it's pointed almost at zenith. But if it were pointing closer to the horizon, the back end where the eyepiece used to be, or now the photographic plates thing would be, that would be way up in the air. So to solve this problem so that astronomers could actually, particularly when it was first built, it was an eyepiece instrument, so that astronomers could actually use this thing, instead of bringing out a ladder, which is just a pain to deal with, the floor is actually an elevator. So as the telescope goes, points towards the horizon, the floor actually rises to keep the same distance between the base of the eyepiece or base of the telescope where the eyepiece is and the floor, to keep that distance constant, which I think is just super, super cool. Anyway, another problem, but the main problem for refracting, and this is the reason why Yerkes still has the distinction of being the largest refracting telescope, even though, as you can see from this picture, it is old. I can't remember how old it is, but it is sort of turn of the 1900s kind of old. Whoops. Is that a lens is supported by its rim or by its edge, and it is thickest in the middle. Well, because gravity is a thing, you know, if this thing is pointed up, which hopefully it will be most of the time, if not all of the time, when this thing is pointed up, gravity is going to cause that lens to deform. It's going to cause the center of that lens to bend downward. So basically, like I said, it's held off by the edges, but the center has the most mass. The center is going to dip. It's going to basically deform. And when the lens deforms, obviously it can't be brought into good focus. And a meter, which is what the Yerkes telescope is roughly a meter in aperture. That lens is a meter in size. So imagine a piece of glass, basically a lens like you have in your eye, your glasses, that has a friggin' meter in diameter is in there. If you have a piece of glass larger than that, then the glass really loses its structural integrity. It cannot hold its own shape given the effect of gravity. So that is the primary reason for why refracting telescopes are no longer used as research instruments. Even though, even to this day, a refracting telescope, if you were to compare the crispness, the quality of the image, this is really a very subjective sort of quality. A refracting telescope beats a reflecting telescope any day of the week. it's just the star field in a reflecting telescope is more crisp. The colors are more vibrant. Oh, it is beautiful to see it. But unfortunately, it is far more expensive to build a larger refracting telescope than it is to a refracting telescope. So even commercially, most telescopes are still reflectors because they are just cheaper to make. So let me do this. The designs. There you go. All right. Good. 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 All right. It's not the best picture, but let's see if this is better. Yeah. Come on. Yeah. Whatever. Come on. Nope. Whatever. All right. I will just. Nope. Nope. Oh man. Oh man. All right. I think that's the best I can do over here. All right. Well, you can. No, that's kind of sucks. Hmm. There we go. Haha. Rob can tech. All right. Don't worry, Sir Little Wolf. You can be rated X if you want to. I do not kink shame. So when it comes to reflecting telescopes, I've already shown you one design, which is the Newtonian, which is the B, this particular telescope. So again, light comes in from the top of the tube. It hits a curved mirror at the bottom, reflects up to a secondary mirror near the top of the tube, and then out a observing port here, which again can be an eyepiece or a CCD camera or a photographic plate back in the day or what have you. You can also have a telescope which is called a prime focus, which is no longer used. But the idea here is that it's just simply a single mirror. And so the light comes in from the top of the tube, gets reflected, and you basically have your instrument at the top of the tube. One of my professors actually had the honor of writing in the prime focus cage of the 100-inch Hooker telescope, probably the worst named telescope I could think of. It's this immense telescope, and he basically got to ride in the middle, right in this literal cage in the prime focus, and because the eyepiece was there, the instrument that he was using was located there. Of course, he was asked, "Well, how did you pee?" And he said, "Well, you brought a thermos and you drank it, and then you used the thermos, to basically refill it." So anyway, that's the prime focus. That's really not used anymore. If you put a camera there, that is also what is known as a Schmidt camera. If you put a detection device there, like I said, a camera, a CCD, or a photographic plates or whatever, that telescope then gets the name Schmidt camera. There's the Cassegrain focus, and that is the most common that I've run into. The telescope we have here, and including the smaller telescopes we use for the lab, are Cassegrain design. The light comes in, hits a mirror at the bottom. That mirror goes up, or that light gets reflected up, hits another curved mirror, not flat like with the Newtonian, but a curved mirror, secondary, and that light gets redirected down through a hole in the primary. and so your instrument is in down here. The reason for use, though, the reason why Cassegrain focus was designed and Newtonian focuses aren't really used anymore is if you have a Newtonian focus, a Newtonian telescope that is large, say like a 30-inch telescope. Back when I was an undergraduate, I got to use one of these. That Newtonian focus is way off the ground. So again, you have to use a ladder in order to get up there if you have to manually manipulate anything. Like I did. Because I was the undergraduate, I got to be the monkey on the ladder turning the filter wheel, which was, well, great fun. So Cassegrain focus put the detection device on the bottom of the telescope, which is far easier to be accessible. And then finally, you've got what is known as the Coudet focus or Naismith focus, where the light comes in, hits that bottom mirror, goes up, hits that secondary mirror, comes back down, hits a tertiary mirror or flat mirror, and that comes out comes out the side of the tube. And that you can either place your camera there, and that's what we refer to as a Naismith's focus, or you can have the beam continue out and actually get redirected underneath the telescope into what is known as a Coudet room. And that way you can put a spectrograph, which is a very sensitive instrument that really doesn't like on a telescope pointing willy-nilly. So you can have a spectroscopic instrument or spectrograph in the basement of your observatory, and that this type of focus or this type of telescope will allow that beam of light to constantly be redirected into the spectrograph regardless of where it's pointing. So there you go. Right in the cage on top of a Hooker telescope, yeah. Now, I think it was Cygnus asked, what about that secondary mirror? Why doesn't that cause a problem? And yes, it does. So while we say that, for example, the 32-inch telescope is a Cassegrain focus. It has a secondary mirror, and there's a hole in the primary. So if we were to compute the light collecting power or the amount of light that is collected by that telescope, it wouldn't simply be a circle. It wouldn't simply be pi 32 squared. We would actually have to subtract out what we call the obscuration of the central the secondary mirror. We'd have to take that out. We'd have to basically subtract that out of the light collecting area. So when designing telescopes, that is one of the considerations that you need to take into account is how big do you want to make that secondary mirror? Because the larger you make it, the more obstruction you have, the more aperture you're essentially cutting out of your telescope. All right, so let's go back to ye old slides. So yeah. Aberration. Advantages of reflectors. Reflecting telescope, obviously the mirror can be supported from the back, which means that you can theoretically build as large a telescope as you can think of, as you can manage. You no longer have flexure or gravity really being playing a major role or being a limiting factor in this case. So you can build as large a mirror as you can. Now, the largest single element mirror that has ever been made or ever been blown, I guess, or created for an astronomical telescope is 5 meters, and that is in the Palomar Observatory near San Diego. Nowadays, very much like the JWST, and I will bring an image of that up. This is people probably have seen this quite often, but I will show you anyway. Share screen. Plop. Nope. Plop. Yep. So, let's do this. Ha ha ha. Wah. I love my sound effects. All right. So, here we have an example of, again, the Hubble mirror and the JWST mirror. The Hubble mirror was roughly around 2 meters in size, or 2.5 meters in size, and it was a solid piece of glass, single piece of glass. The JWST is roughly 6.5 meters in size, and is what we refer to as a segmented mirror. So it is now easier, or more cost-effective, shall we say, to build a large mirror by building smaller segments and then putting them together like a honeycomb. So it is made up of 18 mirror segments, each about a meter, I believe, each about a mirror in diameter, although they're hexagonal, so diameter is kind of a kludgy way of putting it, but basically a meter in size. And that's how large telescopes are now built, is using that segmented nature. And there are two reasons why we do it that way. One, as I've already stated, it's basically more cost effective. It is easier to spin up a small mirror and manufacture a small mirror, lots of small mirrors, and then basically combine them into a single dish or single mirror than it is for a small one. And also it has implications into adaptive optics, which I don't think I will have time to get into today, but we'll see. Well, actually, I can guarantee you we won't have time to get into today. But so that's why those telescopes are built that way, segmented. Okay, let us get into interferometry. And I'm actually going to not start off. So interferometry is the process of taking light from multiple telescopes and combining them to gain angular resolution. And I am going to not start with the radio people who actually developed this, the technology for this, because radio astronomers are dirty, dirty cheaters. They have it way too easy. Radio astronomers can observe during the day, which is, no, that's cheating. They can observe during light cloud cover. I've even heard of them observing in the rain. No. Radio astronomers, dirty, dirty cheaters. Anyway, I digress. But let's talk about interferometry. Interferometry, as I said, is the process of using multiple telescopes, observing the same object, collecting light from those telescopes, and combining that light in such a way as to simulate a telescope with a mirror or a collecting area as large as the separation of those telescopes. So this is a European interferometer known as the VLTI, or Very Large Telescope Interferometer. Like I said, astronomers are super original with their namings. It is made up of 4 elements primarily. It is made up of 4 primary elements. Each of these is an 8-meter telescope, so they are pretty beefy. And they're separated by a distance of, so the one in the front and the one in the back, they're separated by a distance, if I remember correctly, of about 120 meters. What that means is by combining the light of those 4 telescopes, you can simulate the angular resolution of as if you looked at that object using a telescope with a mirror that is 124 meters in size. That, if you remember back to this equation, interferometry, the equation is a little bit different, but basically the same, or basically the same kind of form, is instead of D, you have what is known as baseline, or the separation between the 2 telescopes. The larger the baseline, the better the angular resolution. So instead of getting angular resolutions of arc seconds, which is typical for an 8-meter telescope or a 10-meter telescope, you can get angular resolutions down to milli arc seconds, or 1/1000th of an arc second. Now, what can you do with that? Why is that important? Well, these images were taken by, or these images were created using the char array. The char array is, if you've seen the thumbnail for this particular video, that is Mount Wilson. That is the Mount Wilson Observatory just north of Pasadena, LA. Right now, it's probably covered in snow. There are 6 small telescopes. So the big honking one in the middle, that's the Hooker telescope. That's the 100-inch. And then there are 6 really R2-D2 looking telescopes that are arrayed out on the mountain. We can combine the light from those telescopes in real time, and the longest separation is 331 meters. So what we can do with that is now we have extremely high angular resolution. So as I said in the beginning, stars, if you were to use Keck, which is the largest telescope, well, the Keck pair, each one is 10 meters in size. Those are the largest telescopes we've ever built, at least in the optical. Those would only be able to see a star as a point. They would not be able to see the surface of the star. In fact, aside from the sun, the only star that has ever been resolved in any way with a single telescope is Hubble was able to see the surface of Betelgeuse, kind of, sort of, because Betelgeuse is really close and really huge. But this is the cool stuff. Now, I geek out about this because this is my jam. This is what I got my dissertation in, is using interferometry. Because this is awesome. Altair. When we think of stars as being big balls of gas. That's not always the case. Altair is rotating so fast, so quickly, that it is literally squashed. It is noticeably not spherical anymore. It is a oblate spheroid. The equatorial radius is far larger than the poles. This is something that was implied through observations, but it was not confirmed until we got a direct observation, a direct image of Altair using the char array. There you have Betelgeuse with basically there what you're seeing is those 2 bright spots. Those are literal bright spots on the surface of Betelgeuse. At some point, I may bore you all with my sort of my kids' pictures of Lambda Andromeda, where I actually was able to resolve dark spots on the surface, and I actually was able to see them rotate across the surface. So cool. But probably the coolest thing was done by a guy that I used to observe with. He and I would actually compete to see who could get the most data. He was looking at a star called Epsilon Aurigae. And Epsilon Aurigae was just one of these one-off bizarro stars. From photometry, it would lose light. It would lose a tremendous amount of light for a few days every 27 years. We really had no idea why that was the case. Well, it was a mystery, and one of the solutions was, all right, maybe it's a binary where you have this really big honking cool giant star, and then around it you have a smaller bluer star that is encapsulated into a disk. And that was the idea. And then Brian comes along, uses the char array to image the thing, and you can see this is not a model. This is an image of the disk coming into view and eating out, basically blocking the light from that star. You can't get this anywhere else. JWST can't do this. Only interferometry can do this. So awesome. Interferometry has also allowed us to do things like this. So we know that, and again, this is in here because it's my slides, and I love young stellar objects or protostars. We know from, again, indirect methods, we know that stars, when they form disks around them, disks of dust and gas, from which planets then form. We knew that indirectly from other observations, but Hubble was able to observe or image a few of them, but really only in very specific orientations where the disk is kind of in line, and so these dark stripes you see through these apparent clouds of gas, that is the protostar being the light from the protostar being obscured by that disk. So we could tell, we now have observational evidence that tells us the disk exists, that it exists, but we can't really see anything of it because we're looking at it edge on. We really can't see if there are structures inside that disk, that sort of thing, until we came up with until we built the ALMA interferometer, which is millimeter radio. But they were able to look at a young stellar object that Hubble could not resolve. And they got this image on the right. And we've done this now for half a dozen, if not more, other objects. And we are looking at a disk of material around a forming star. And you might notice these dark rings that go through here. Those dark rings are an absence of dust and gas. The best explanation we have for why those rings should exist is because there is a planet, a protoplanet, going around, literally throwing its mass around, evacuating those regions. We are literally looking at an image of planets that are forming essentially in real time. So again, without interferometry, we don't get this. We are not able to see this. And then lastly, I don't have an image of it, but if you Google it, well, actually, I've been doing it all day. So let me do this. The last really cool image, M87, Blackie Holy. Show. Presents. Share screen. That one. Hopefully, you've all seen this before. This is the image taken of the black hole, supermassive black hole at the center of the active galaxy M87. This is the first time that a black hole, or rather the environment around a black hole, has been imaged. Again, there's another reason why radio is dirty, dirty cheaters, is that in interferometry, when you talk about optical telescopes, you actually have to combine the light in real time. So you're limited in the separation between these telescopes. Not so much in radio. You can just observe an object, record your data, wait for the Earth to rotate so that another telescope comes into view. It observes, records the data, and then you can basically wait until you get enough telescopes to do this sort of thing. And you can combine that data later from all of these different telescopes. And that's basically what the Event Horizon Telescope is an array of, I think it's around a dozen radio telescopes around the globe, combining the light that they collect from the center region of M87. And they now, by combining that light, they can simulate a telescope that has the diameter of the Earth. So you can imagine what the angular resolution of that would be. And that is how they are able to see something that is roughly the size of our solar system in something that is millions of light years away. And so again, the only way that this is done is through interferometry. All right. Very large planetary racetrack. Actually, it's a kind of a running joke to try to come up with these acronyms. I'm going to put this in chat, and you can kind of put this in. So, I think they should build a interferometer and call it the super huge interferometric telescope. There you go. That would be the super huge interferometric telescope. Anyway, that's my. I will keep my potty humor to myself after this. So anyway, so that's all for today. Basically, that covers the basics of telescopes, their designs, essentially why we want larger and larger telescopes, because that allows us to have finer detail or see finer detail in our objects, be able to see things that we would never be able to see before, because again, before the advent of these larger telescopes, or more specifically interferometers, we could detect the light from say that supermassive black hole, but we couldn't resolve the light from that supermassive black hole, or from Auriga or Epsilon Auriga or Altair or Lambda Andromeda. So the larger the telescope that we have, the better the angular resolution, the more detail and the more physics we can see. Also, the larger the telescope, the fainter objects we can see, the more light we collect, the fainter we can see, and that means the further into the universe that we can see, the further back in time we can see. So that basically covers today's lecture. Next week or next time, which will be maybe tomorrow, probably Wednesday, I will talk about how the atmosphere affects ground-based observations, what limitations it makes, what the limitations are, what types of astronomy cannot actually be done on the ground, and how is it that we can mitigate the effects of the atmosphere on our observations. And then if I have time during that lecture, but I probably will split it, the third lecture will actually be on detection system, or detection devices like CCDs, photographic plates, that sort of thing. So, is there going to be a test? For my 111 students, yes, there will be a test. It's the final exam. But for you all, no. Unless I can send you the exam if you want to take it. But anyway. So yeah, that's the lecture today. I do want to show some people some things, because I remembered I talked about this during the live stream last night, and I just remembered that I wanted to show people this, so I'm going to go get it and I'm going to come back. So hold on. Oh, I'm sure you do great, little wolf. Oh, wow. I don't think I've... I actually don't think I've looked through all of these. Let's start with This, yes, astronomers do it all night long. Physicists do it with charm. This is a photographic plate. This is basically the first time that astronomers were able to record data for posterity. Like I said, I'll go into a little bit more when I talk about this, and probably the not the next lecture, but the lecture after that. It's kind of hard to see. These are very dirty. I really do need to clean them. So this is, like I said, a photographic plate. This is the Ring Nebula. This is a planetary nebula. You can see that bright point in the middle. There are some arguments as to whether or not that's actually the white dwarf that created, or that is the remnant of this Let's see, this gas that gas, when put back onto that white dwarf, would actually be a star very similar to the sun. And so this is what a photographic plate actually looked like back in the day. Well, looks like now. So that's the Ring Nebula. That's the Crab Nebula. You can see the little stars here in the background. What I want to do is I want to clean these up, and I would like to build like a frame that is backlit so that I can just basically display these. And you can see the Crab Nebula. You can see the fine filamentary structures. This is a supernova remnant. I don't know what the provenance of these are. They were in my office, buried in my office in Louisiana, and I just decided that they accidentally fell into my stuff when I left Louisiana. So I asked around where this came from. No one could tell me. Haha. This is the Orion Nebula, my favoritist object. This is a star-forming region in the constellation of Orion. And so, you can see the huge nebulosity that comes off of this. Ooh. Is this what I think it is? Yeah. Wow. That is a solar prominence. Actually, this may be a coronal mass ejection from start to finish. You can see the left-hand side, this side, that's the sun. This arc right here, that is basically a bit of the sun being exploded outward. And then here you can see it getting exploded outward later. Here, the surface of the sun. And then even more in time, you can see that it's exploding outward even more. When we talk about the sun, I'll talk about what a coronal mass ejection actually is and how kind of scary they are. So, but yeah, this is actually pretty awesome. Yep. Crack that. This one is broke. I don't know if I want to actually put those away. And this one, I don't even know how this was made. This appears to be ground, and then superimposed on it, I really have no idea how this was made. Those are images of the moon. Those are images of the full moon as it goes from horizon upwards. So it's like they exposed, they stopped exposing, they waited, I don't know, an hour, maybe half hour or whatever, exposed again, and kept doing that. I would have thought that would have. I didn't know if photographic plates were you could do that with photography, but it's pretty awesome. So, like I said, I'll get into more of um, more of how these are made, what these are, and how they are made, and why we eventually stopped using them as a thing. So. I once seen a metal plate with holes and fiber optic cables for each. Yes, actually, that is how. So, in one of my other streams, I talked about using galaxies or mapping out galaxies and finding out the redshifts of galaxies. One of the ways that was done, and this was, we have a database of hundreds of thousands of these galaxies. And the way that was done was by an instrument where at the back end where you put a camera, it put a metal mask that corresponded to where those galaxies were in the night sky, and you fed fiber optic cables to each of those holes. So basically, the light from each of those galaxies would get imaged onto the ends of those fiber optic cables. That light would then pass through the fiber optic cable and go into a spectrograph. So you're able to take the spectra of hundreds of galaxies at a time. And that is how we have the Sloan Digital Sky Survey, this knowledge of the redshifts of so many hundreds of thousands of galaxies. It is through that process that we were able to really be able to accomplish that. No, no, I actually don't know where the Eddington plates are. At this point, they would be museum worthy. I would imagine they're actually worth quite a bit of money. So no, they are. I can tell you that none of these are, in fact, Sir Arthur's plates. I have actually never seen or been able to handle photographic plates before. I've seen them in display cases, and I've seen reproductions of them, basically printouts of the negatives of photographic plates. But I've never seen I've never been able to have photographic plates before. So awesome. Awesome. Looks like it was shot using a nice. Yeah. I'm assuming you're talking about the moon shot. So yeah. All right. So yeah, those are my photographic plates. I really hope to one day be able to have the time to you can see they're just gunky. They're just really gunky. I really need to figure out how to clean them without ruining them. And like I said, I really love to figure out a way to display them. Because they are, again, I'm geeking out. They are awesome. Oh, this is a comet. I don't know if you can see it. Oh, somebody has already put a backing onto it, like that, so it would diffuse the light, I guess. So you can see it. I'm glad you're enjoying yourself, little wolf. I'm feeling a little manic today, so I apologize for that. I don't know what comet this is. I really wish you could see it the way I'm seeing it right now with backlit. Oh, it's gorgeous. It's absolutely gorgeous. This is not Hyakutake. I wonder if this is Halley's. I'll have to look. I'll have to compare this to other images of Halley's and see if this is actually Halley's comet. That would be cool. That would be really awesome to actually have a photographic plate of Halley's comet. Wow, that's just awesome. That's just pretty pretty awesome. Anyway, so yeah. Thank you for watching this. Those of you in the future, thank you for also for watching it. Thank you for being here. Well, I realize the process of reversal slime images, so the light bits are light. Yes. Been going full speed today for a change. I love hearing about early Photoshop. Yeah, I've been. I am. Where is it? I am also going full speed at this at the moment. So yeah, it's more, like what I said, kind of manic at this point. I was noticing that too because the reproductions that I see, the photographic plates are always in negative. They are dark spots on a white field, and so yeah, these I will have to really look into this. Like I said, photographic plates. I know them in theory. I know basically enough to teach about them, but I don't know the nitty gritty details of it. So if anyone out there has knowledge of photography, please let me know what you think of these, and figure out how they've been processed. But if so, that'll be the end of the lecture today. Next lecture will either be tomorrow, most likely Wednesday. It will be continuing on telescopes, like I said, specifically how the atmosphere affects telescopic observations on the ground. If you like these lectures, this is part of a lecture series called The Solar System, where I go into, it's still introductory astronomy, but I go into a little bit more depth than I do in my survey course. If you like this sort of content and you want to see more of it, I do plan on, I'd like to be able to continue this with stars and galaxies. I'd also like to do something similar to this in other fields of astronomy, cosmology, and also physics. I also like to be able to teach be able to create an introductory algebra-based physics series as well. So if you like this sort of thing, please like, share, and subscribe. If you'd like to help me out or help the observatory out in terms of our public outreach financially, please consider becoming a Patreon. You can find all that groovy information on my About section on my channel. You can also find my Discord link, which I should probably also advertise. My Discord link. I have a Discord channel of my own. I have a class Discord channel, but that link is for my own personal Discord. So if you want to basically come find me and just hang out with me on Discord on my server, please go ahead. Feel free to look into that. Anyway, so as always, peace out, clear skies. Catch you on the next one.